Hi, I am MD Fayaz Abdullah Saidi, the presenting author of paper ID 465. The title of our paper is MosquitoMiner, a lightweight rover for detecting and eliminating mosquito breeding sites. This is the table of contents that I am going to present in the following slides. The motivation of this paper is that we know that mosquito-borne disease pose a significant threat to public health all around the world. A website called Mosquito Reviews claims that mosquitoes are responsible for over 1 million deaths each year, and 700 million people get ill each year by mosquitoes. Another organization called Buzz Off Organization published a report where they show that mosquitoes are the leading cause of yearly human death caused by any other creature in the world, which is more than the human themselves. Also from this graph, we can see that the dengue is the deadliest disease caused by mosquitoes. Another motivation of our project is the ineffectiveness of the conventional methods where we have to do a lot of manual labor. As a result, we need an innovative solution to early detect and eliminate mosquito breeding sites. The objective of this project is to design and develop an autonomous, lightweight, and cost-effective unmanned ground vehicle, also known as a rover, that is capable of detecting and eliminating mosquito breeding sites using different machine learning models trained on our custom dataset. In the related work part, we have benchmarked several research projects. Here, all the projects actually worked only on detecting the breeding place, but they didn't work to perform any action to eliminate the possible mosquito breeding grounds. Moreover, none of them are actually open sourced, which means none of them actually provide any code or their dataset. And two of them didn't actually care about the cost to build the project. Unfortunately, none of them actually focused on the robustness of the structure to make it lightweight. Here in the figure, we can see that the structural difference, the structure we used is called warm electronics box or web structure, which is actually proposed by NASA. So from this, we can actually say that our method is so far state of the art. We have divided our methodology part into two major sections. One is system overview and another is software architecture. So for the system overview part, first of all come the hardware components. In the system overview part, we have divided it into 5 subsections. From the exploded view of the rover, we can see the hardware components that we used here, like we used GPS module, spray module, Raspberry Pi 3, camera, then ultrasonic sensor, Pixhawk, Arduino, then motor, wheel, then power module, etc. Then it comes the data acquisition part. So the rover's journey actually started with its camera capturing visual data of the surrounding environment, and the GPS module continuously acquires the rover's location. All this data are then transmitted to the Raspberry Pi, which is the central processing unit of this rover. So this information is very crucial for navigating, tracking movements, and potentially creating the maps of breeding sites. Also, the Arduino microcontroller collects the data from additional sensors like ultrasonic sensors for object detections and sends it to the Raspberry Pi. For the data processing and data decision making part, the Raspberry Pi receives all the data and utilize object detection models and different type of algorithms to identify potential mosquito breeding sites and make crucial decision about the rover's action. Then movement and elimination is based on the decision making process. Control signals are transmitted to the Raspberry Pi to Arduino. Then from the Arduino, the data or signal is transmitted to the motor driver. Then it regulates the left and right motors based on their signals, causing the rover to move forward, backward, turn, or adjust the speed towards or away from breeding sites while potentially avoiding the obstacles. So upon reaching the breeding site, the rover sprays larvicides using the spray module. We also keep the human intervention part, where the operator can take manual control of the rover's movement using the remote controller. Then it comes the software architecture part, where for the data flow and communication, first of all, it comes the software components. So the components we used like OpenCV library, YOLO V8 for object detection, then the operating system of Raspberry Pi. Then it comes to the data flow and communication. Firstly, the captured video data is passed through the OpenCV library to process the data to make it compatible with the machine learning models. Then the YOLO V8 model analyze and pre-process image data to detect and classify potential mosquito breeding sites within the frames. For automation, it uses the map proxy or mission planner to send commands to the rover to autonomously navigate waypoints. This project uses wireless communication UDP data, user datagram protocol system between the Raspberry Pi and the mission planner to broadcast the data. We also use the IC2 protocol to connect Arduino and Raspberry Pi. For the result analysis part, we have divided it into three subsections: detection accuracy, elimination accuracy, and operational accuracy. For the detection accuracy system, we used YOLO V8 pre-trained model and fine-tune it on our custom dataset and achieve a mean average precision of 61.7%, indicating a moderate level of accuracy in detecting relevant objects. And we also get the high precision of 84.7% and recall of 51%. And here we can see some of the good examples of detecting real-time detection in various environmental backgrounds. Then for the elimination accuracy, we introduced two new matrices to evaluate our rover. They are, first of all, the target class reduction rate, which is used to quantitatively assess the effectiveness of our autonomous rover in reducing mosquito population in targeted breeding sites. For this study, we designed a controlled environment. The setup includes 5 distinct artificial breeding sites, each created to represent common breeding habitats. The rover successfully identified and reduced 4 out of 5 breeding sites. Here, the 5 breeding sites are presented as P-pre or pre-treatment population, and 4 are P-post, which means post-treatment population. And if we calculate TCRR, it will be 80%. Another one is area coverage, which is to examine the area coverage capability of the rover. To do this, we incorporate predetermined path within our experimental setup marked by 8 nodes or checkpoints. So the success of the navigation was measured by the rover's ability to reach these points without manual interventions. The rover successfully reached 6 out of 8 checkpoints, which we can calculate to 75% success rate in area coverage. For operational efficiency, the battery life of the system is robust because we didn't have to charge it within the mission, and still the battery has more than half charge, which allows us to extend our operation before requiring a recharge. In our control test environment, the rover completed its mission through the predetermined path within only 9 minutes and 43 seconds, which is quite impressive. The cost effectiveness of the rover is also notable, with the total operational cost being around 410 USD, which is shown in the table. So the future work of our project is to upgrade our hardware components, as we have used Raspberry Pi 3, which is not state-of-the-art component. So there are Raspberry Pi 5 already in the market, or more robust components, microcontrollers like Jetson Nano. So we will try to upgrade our hardware components for more robust detection. We also will try to enhance our data set for understanding different types or patterns of breeding place, as we have only one class that will just detect the breeding place, possible breeding place, but it cannot differentiate between the patterns of breeding place. Then we will try to enhance the structural or architecture of the rover, which will help us to make a more strong rover, and we will also try to make it waterproof. So in conclusion, we can can say that we have already built a promising, novel, and innovative solution for controlling mosquitoes. And by using different advanced algorithms and techniques and autonomous control strategies, we have already demonstrated the efficiency of our implementation rather than manual labor methods or the traditional methods for public health. Thank you.